Hello and welcome to Lesson 4 in Section 2 of this chemistry course. Now, at the moment we're looking at chemistry of the elements in Section 2, and today we're going to look at the reactivity series. So reactivity series, a bit more content on here. Going to start first of all looking particularly at reactivity series, then going to go on and look at oxidation reduction, and think about terms like redox, oxidizing agents and so on, and then finally looking at rusting. So a lot to get through. Let's make a start by thinking first of all, what is a reactivity series? Well, you can guess a little bit from the title, but reactivity series places metals in order of their reactivity based on how vigorously they react with water and dilute acids. So the more vigorously they react with water and acids, the higher they are up the reactivity series. Let's look at the list of metals. Now we've got a list of metals going from gold here to potassium here, and what we're seeing here is an increasing reactivity. So we've got the group, the increase in reactivity. And the first ones here, potassium, sodium, lithium and calcium, these are very reactive metals. Next group of guys, magnesium, aluminium and zinc, are all quite reactive. Then we've got iron, tin, lead and copper, which are not so reactive. At the bottom here we've got silver and gold, which are very unreactive. Now we use these lots in jewellery, don't we, silver and gold, so it's a good job they're reactive. Unreactive. What you don't want is these reacting with water, or that when you're wearing your jewellery. So these are very unreactive down here. Let's start looking at some of the reactions, shall we? First of all, reaction with water. You've probably seen these guys before, potassium, sodium and lithium. When you add these to water, you get a pretty vigorous reaction. Okay, so potassium is a very violent reaction, sodium a bit less so, and lithium again a bit less so. But in each case you get a violent reaction with water forming hydroxide. The metal will fizz and hydrogen will be released. Now the equations are pretty much the same in each case. Let's look at the first one, potassium. So potassium is K plus 2H2O water. There's a hydroxide, potassium hydroxide in solution, and look, hydrogen gas is produced. For sodium, Na plus H2O gives NaOH and hydrogen. And lastly, lithium plus water, lithium hydroxide and hydrogen. Note in each case here how they're balanced to make sure we get equal numbers of atoms on the left and on the right. Now the middle group here, calcium and magnesium, they will react with cold water, but quite slowly. Magnesium, and in fact very slowly, but again they form the hydroxide. And again you'll see bubbles of hydrogen gas. Similar equations, calcium plus water gives calcium hydroxide and hydrogen. Magnesium plus water gives magnesium hydroxide plus hydrogen. Now these guys in the middle here don't react with cold water at all. However, you can get them to react with steam. And at the top here we've got the apparatus. If, for example, let's take iron, which is here. If you put some iron into a tube and you make steam flow over the iron, okay, steam, which is, don't forget, which is very hot water, isn't it? So steam's flowing over the iron, okay. As it does so, a reaction will take place with the iron, and again you get hydrogen gas being produced. But in this case you don't get a hydroxide, you get the oxide. So for these guys here, aluminium plus water gives aluminium oxide plus hydrogen. Zinc plus water gives zinc oxide plus hydrogen. Iron plus water gives iron oxide plus hydrogen, and the same will happen with tin. So those react with steam as opposed to cold water. Now these guys down here, no reaction with water whatsoever. Okay. Now we said at the beginning we had to look at these in the reactions with water and with acids. Let's look now at the reaction with acid. Yeah, well, I don't think I'd want to be around when these are added to acid. Imagine how these react with water. You can imagine that with acids they're much more violent. So these elements react with acid in a very violent and dangerous manner. Now these are not the sort of experiments you would attempt to see in the school laboratory. So if you are at school, please don't make your teacher do these, because they won't be able to. In each case you get the salt being formed. So potassium plus hydrochloric acid gives potassium chloride, again hydrogen. Remember how we tested hydrogen? Remember that? It's burning splint, goes into the tube. What do you hear? You hear a pop. That's right, squeaky pop. Sodium plus, in this case, sulfuric acid gives sodium sulfate plus hydrogen. And lastly, another example, calcium plus nitric acid gives calcium nitrate plus hydrogen. These are salts. Potassium chloride, sodium sulfate, calcium nitrate are all salts produced from the acids. Okay, I just used these acids as examples. You could have used potassium with sulfuric, potassium with nitric, doesn't matter. But I use these as examples so you can see which salts are formed from the acid. So, violent reaction between these guys at the top and acids. Stay well away. Now these here in the middle, these react reasonably well with acids, and the reactivity, as you'd expect, decreases going down this way. So magnesium is the most reactive, all these here, and again magnesium plus hydrochloric acid will give us magnesium chloride plus hydrogen gas. You got it. Zinc plus sulfuric acid in this case here gives zinc sulfate plus hydrogen, and I've chosen tin down here. Tin plus nitric acid gives tin nitrate plus hydrogen. Note the salts. From hydrochloric acid you always get the chloride, from sulfuric acid you always get the sulfate, and from nitric acid you always get the nitrate. Okay, so worth remembering those. And you've got it, these guys at the bottom here, they don't react with acids at all. Now we can consider start again, shall I? We can consider here how these metals here react with each other, and that's called a displacement reaction. What's a displacement reaction? I haven't got a clue. Let's have a think what the teacher says. Now the teacher says a displacement reaction is one in which a more reactive metal displaces a less reactive metal from a compound. So here's the reactive guys up here, and they'll displace the less reactive ones here from a compound. So in other words, a metal higher up in the reactivity series, that's this end here, will push out a metal lower in the series that's down here. Okay, so effectively they will bully and push these out, won't they? Now we need to know two things. We need to deduce the position of a metal within the reactivity series using displacement reactions between 1. Metals and their oxides, 2. Between metals and their salts aqueous solution. Let's look first of all at metals and oxides, shall we, by looking at a classic example. Now here we've got a displacement reaction. Here we've got a mixture of aluminium powder and iron oxide. Now just left mixed, nothing really happened. We need to have a little bit of a boost, and we kick them into action, don't we? So for that we use magnesium ribbon fuse. Magnesium is there simply to get the reaction started. We're looking at the reaction between aluminium powder and iron oxide. Now think about it. Where's aluminium? There it is. Where's iron? Down here. Right. You see what's going to happen? Aluminium's going to come along and it's going to kick iron out of the oxide. A very violent displacement reaction occurs, and when it's all over, you're left with pure iron here. So this here must be aluminium oxide, mustn't it? Let's have a look, shall we? Aluminium plus iron oxide gives aluminium oxide plus iron. We were right, weren't we? We said, because aluminium's higher here than iron, the aluminium here will kick out the iron from iron oxide and take its place. So we've got aluminium oxide plus iron. Let's look at the equation. Al plus FeO gives Al2O3 plus Fe. You can see there that we've had a displacement. The aluminium has displaced the iron from iron oxide to form aluminium oxide and iron itself. Okay, the second stage was between metals and their salts in aqueous solutions. Let's look at an example. Now here we've got copper sulfate solution, lovely blue colour. We're going to stick into it an iron nail. Now think, where's iron? There's iron there. Where's copper? Down there. Iron is the more reactive of the two, isn't it? So can you see what's going to happen? Okay, iron is going to kick copper out of its solution. So what happens? A displacement reaction occurs. And look, there's the copper being formed. So left to run its course, you find you're left with green iron sulfate solution, and the copper is now being displaced, and you find it as a deposit on what's left the iron nail. So a displacement reaction occurs because iron is higher than copper in the reactivity series. Let's look at the equation. Copper sulfate plus iron gives iron sulfate plus copper. Or in other words, CuSO4 plus Fe gives FeSO4 plus Cu. So iron is there, copper is there, iron displaces the copper, kicks it out and takes its place. FeSO4 plus Cu. Now, little challenge for you, okay? Little challenge for you, get your brain thinking. Now, I want you to think, and don't please go to look at the answers, have a go yourself. Pause the video and have a go. If you've got a solution of iron sulfate and you put some lead in, will a displacement reaction occur? Copper sulfate, lead. Zinc sulfate, iron. Copper sulfate, tin. So, will displacement reaction happen? Have a go yourself. Now, don't cheat, because I'm watching, okay? So pause the video, have a go. Right, I'm trusting you here, you didn't cheat, okay? Will lead displace iron sulfate? No, because lead is below iron. Will lead displace copper from copper sulfate? Yes, because lead is above copper. Will iron displace zinc from zinc sulfate? No, because zinc is above iron. Will tin displace copper from copper sulfate? Yep, because tin is above copper. Okay? Well, I hope you got on well there, and you got, hopefully, 4 out of 4. Right, let's change tack now and look at something called oxidation and reduction. Now, in this section here, you need to understand oxidation and reduction as addition and removal of oxygen, respectively. Okay? Oxidation, respectively. Okay, let's look, shall we? Now, little man tells us that oxidation may be defined in 3 ways. Oxidation is addition of oxygen to a substance. Oxidation is removal of hydrogen from a substance. And oxidation is the loss of electrons from a substance. You may have come across an oil rig. If you come across an oil rig in one of my other videos, this is this here, isn't it? Now, we're only particularly interested here in the first one. Okay, oxygen. Let's look at an equation. Here's some examples of oxidation. Now, sulfur plus oxygen gives sulfur dioxide. You can see there the sulfur is being oxidized because it's gained oxygen. Carbon monoxide plus oxygen gives carbon dioxide. You can see there that the carbon monoxide is being oxidized because it's gained oxygen. Okay, so there's oxidation. There's oxidation there, as shown by the addition of oxygen. Now, reduction may be defined in 3 ways. Reduction is removal of oxygen from a substance. Reduction is addition of hydrogen to a substance, of hydrogen, and reduction is a gain of electrons. Now, again, we're only interested here in the first one, the removal of oxygen. Now, here's lead oxide. Now, you see here that when lead is heated, it loses some of the oxygen. So we get Pb3O4 goes to PbO plus O2, oxygen's been removed. And again, with sodium nitrate. Heated, you get sodium nitrite. This is nitrite. This is nitrate, ATE, nitrite, ITE plus oxygen. So in both cases there, they have been what we call reduced. Okay, let's look at these terms. Redox, oxidizing agent, reducing agent. Now, first of all, what is redox? We may have come across this before. We looked using electrons and electron gain loss, but we're thinking about something else today. So let's go to the monitor, shall we? Now, in a redox reaction, both reduction, you can see RED there, and oxidation, OX, occur. RED, OX. For example, when hydrogen is passed through a heated copper oxide, copper and water vapour are formed. Now, I think we need to look at the experimental setup here. Let's go to the setup, shall we? Right, what we've got here is, here's copper oxide. Okay, here's copper oxide. Now, if you pass dry hydrogen over copper oxide and you heat it, a reaction occurs. Now, this is anhydrous copper sulfate. I'll explain why we got this in a moment. What happens then is excess hydrogen be removed this end here and burnt off. But the key thing is that hydrogen is being passed over heated copper oxide. Let's go back to the monitor. Now, in a redox reaction, okay, we know both these occur. Now, the water vapour that's produced in this reaction, okay, going back to the reaction here, copper oxide is being reduced, water is being produced. The water vapour can be trapped by the anhydrous copper sulfate, turning it from white to blue, and excess hydrogen is burnt off. So this is what's happening in the reaction. Copper oxide is heated, hydrogen is being passed over it, the hydrogen is stealing oxygen from there, left with copper plus water. So can you see, hydrogen itself is being oxidized because it's gaining oxygen, but copper is being reduced because it is losing oxygen. This is what is called a redox reaction. A redox reaction because you've got both reduction and oxidation happening simultaneously. Right, back to the spec. The spec says, what's an oxidizing agent? Let's define it. An oxidizing agent is a substance which brings about oxygen. It's something that very kindly adds oxygen to something. It adds oxygen. Let's have a look, shall we? Right, here we got hydrogen peroxide. Here's hydrogen peroxide here. Now what this is going to do, this is going to donate an oxygen to sodium sulfite here. You end up with sodium sulfate, so this has been oxidized, and hydrogen peroxide itself is reduced. So an oxidizing agent will give up oxygen and will itself be reduced, but this here has been oxidized. Now the opposite is true of a reducing agent. A reducing agent is a substance which brings about reduction. What it does, it steals the oxygen. Another example, we've got carbon monoxide here heated with iron oxide. Carbon monoxide will steal that oxygen. We're left with iron, so the iron has been reduced because it's lost oxygen. Carbon monoxide has been oxidized to carbon dioxide by gaining oxygen. Got it? I hope you have. If not, go back please and check it out. Now last little section here, we're going to look at a particular aspect of oxidation, okay, which is it described here. We're looking at what's called rusting, and rusting is the corrosion of iron and steel, because what we're forming is an oxide. Rusting is an oxidation process as it results in the formation of iron oxide Fe2O3. Right, now to get rusting you need two things. You need oxygen and water. If either of those two are missing, iron doesn't rust. We can see that in a very simple experiment. Now here's a simple experiment. You've got here an iron nail, and so on. Now in the first setup here we've got, first of all it's sealed, there's a bung in there. We've got anhydrous calcium chloride that absorbs any moisture in the air. Okay, cotton wool just stops it falling down. Now here we've got very dry air, there's no moisture at all. Does it rust? No, it doesn't. In this one here, what we've got boiled water, and if you boil water, what you do is you remove all the oxygen. So in here, beneath the little blue line there, we've got water covering the nail. Now boiled water contains no oxygen. The Vaseline layer there is to stop any oxygen from getting into the boiled water, so we can be pretty confident we've excluded any air. So in this case here, air is excluded. Is it rusting? Not in your life. So, moisture excluded, no rusting. Air excluded, no rusting. Right, now cover it in water. So blue line there represents water beneath. Water is present, there's lots of air in the water. Will it rust? Yes it does. So air and water brings about rusting. Now, suppose you put some salt in the water. So here we've got a dilute sodium chloride solution or salt solution. It will rust far quicker. So here we've got air, water and salt. So you live by the seaside and you've got lots of water in the air and salt in the air, your car's going to rust more. It's a pain, isn't it? How can we stop that? Well, let's think about prevention of rusting, shall we? Now, you can do it by painting the surface, greasing the surface, covering oil, or putting a plastic layer on it. These are all well and good so long as the surface is kept intact and not cracked or scratched anyway. Another way you can do it is what's called galvanizing. Now what you do, you get your iron or steel object and you dip it into molten zinc. When you take it out, the zinc forms a layer over the iron and steel. Now as we know, zinc is high in the reactivity series, so long as the surface is intact, it's okay. If the surface is scratched, what happens is, because zinc is higher, it's the zinc that reacts with the oxygen rather than the iron. Okay? Zinc is reacting with the oxygen rather than iron, so it's protecting the iron beneath. Now there's a very special term we have that, it's called sacrificial metals. They are in effect sacrificing themselves. Now here we can see the bottom bit of a boat. I haven't got a clue what it's called. Here's a bottom bit of a boat. Is it a hull? Could be. Bottom bit of a boat here, and here we've got bits of magnesium. Now what happens here is the magnesium is attached to the steel of the boat. Now since magnesium is higher than iron in reactivity series, magnesium reacts with oxygen in preference to iron. So the magnesium in effect is sacrificing itself and being used up. So what you can do, you can put these magnesium bits on here, they'll react protecting the steel and they can be replaced afterwards. Okay, that's what we call sacrificial metals. Right, golly, that was a lot, wasn't it? So in this lesson we've covered reactivity series of metals, displacement reactions, oxidation reduction, rusting. Please go back and watch the sections again if you're not sure, and don't forget to use other resources if need be to make sure you fully understand everything. Okay, thank you for watching this video. I'll be back with you again very soon. Bye for now.